All right, we're going to finish up section 6.7, our word problems relating to rational equations. We've already talked about solving proportion types of problems, similar triangles. We've talked about work problems. And the last type of word problem we're going to talk about are problems involving motion. So speeds and times and distances. And you've maybe heard of distance equals rate times time, where rate is the speed, the time that you go that speed will tell you the distance that you've gone, right? And you can actually solve that equation to get a couple of different versions of that same equation. We can solve it for r, we can solve it for t, but they all kind of give you the same values. Distance equals rate times time. We're going to use one of these similar equations, equivalent equations, to maybe solve some of these motion problems. Let me show you. Example number 7 says, on her road bike, Olivia bikes 15 kilometers faster than Jason does on his bike. In the time it takes Olivia to travel 80 kilometers, Jason travels 50 kilometers. Find the speed of each bicyclist. Are you okay if I call Jason's J and Olivia's O, maybe something like that to define our variables? And I'm going to go through and I'm going to kind of think about the important information in this word problem. I notice that they give me a value here, 15 kilometers per hour. I know that this is Olivia's speed, right? This is Olivia's speed or her rate. It says here Olivia travels 80 kilometers. Isn't that Olivia's distance? And Jason travels 50 kilometers. Isn't that Jason's distance? So I know Olivia's distance, I know Jason's distance, and I know Olivia's speed. We don't know the speed of Jason though, do we? Okay, what do we know? And how can we kind of put this into a math problem? We have some distances, and it doesn't look like those distances are equal, right? Doesn't Olivia go 80 and Jason only goes 50? We have speeds, and we know that those speeds aren't the same. Actually, Olivia goes faster than Jason. And this actual rate isn't actually Olivia's rate, isn't it? It's just how comparing her to Jason. So it doesn't say that she went 15 kilometers per hour. It says she went 15 kilometers per hour faster than. So we've got to be careful with that. So it's not her actual speed, but it just compares her speed with Jason's. But we know that the speeds aren't the same. We know that the distances aren't the same. But what is the same? And this is where you have to be really careful and read these problems really carefully. Doesn't it say in the same time? So Olivia and Jason are riding their bike, and they're riding their bike for the same amount of time. They don't go the same speed and they don't go the same distance, but they do go for the same amount of time. So I'm actually going to use that important information to help me set up an equation. I'm going to say that the time for Olivia is equal to the time for Jason. Their times are equal. That helps me at least start making a math problem. All right, so do we know the time that Olivia went? Nope, we just know her distance and then part of a speed that she went, right? And we don't know the time that Jason went either. So what do we know about time? Well, don't we know back up here that time is the same thing as distance divided by rate? So let's use that idea. Let's say that the times for Olivia are really her distance divided by her rate. And the time for Jason is really his distance divided by his rate. Now, do we know Olivia's distance? Sure we do. Didn't it say that she went 80 kilometers? And don't we know Jason's distance also? Doesn't it say that he went 50 kilometers? So we can actually plug in those values to the distance for Olivia and Jason since we know their distances. Okay, now what do we know about their rate? Again, this is where you have to be careful. We don't know Jason's rate. Can we call that J? And we don't know Olivia's rate, but we do know that she's 15 kilometers per hour faster than Jason. So if Jason is J, can I call Olivia's speed J plus 15 because she's 15 kilometers per hour faster than him? So now I have an equation that looks like this, with all the information from the word problem into a rational proportion, it looks like, doesn't it? I have two fractions equal to each other. So now I can cross multiply and solve and figure out what J equals. J being the rate that Jason rides his bike, right? All right. When I cross multiply then, it looks like I'm going to do 80 times J, and then I'm going to do 50 times J plus 15, making sure I distribute the 50 to the J and the 15. So you should end up with an equation that looks like this. 80J equals 50J plus 750. I can subtract 50J from both sides, and I can divide, and you should end up getting j equals 25. Now remember, the j from your problem represented the rate of Jason. That's his speed. So we need to make sure that we label it correctly. So I know that Jason is going to go 25 kilometers per hour. That's his speed. But the question also asks us for the speed of Olivia also. Well, don't we know that Olivia went faster than Jason? Don't we actually know that she went 15 kilometers per hour faster than Jason? So if Jason went 25 kilometers per hour, then that must mean that Olivia went 40 kilometers per hour. I now know the speed of both of the bicyclists. Whew, kind of hard. There's lots of different interpretation to these problems, so you've got to read it very carefully. Highlight the important information, circle the important information, label the important information, and figure out how it's all related. Are things equal? Do you have a total distance or total time or total, and you can add some stuff together? How are you going to make it into a math problem? And then go from there. All right, make sure that you practice one like that. We'll do another example in the next video.